Yeah. Either find a grad student. Well, you know, I can draw the block diagrams of what I want, and I can break down the modules for what I need. And if I can find somebody who really likes doing FPGA design, I can build it. I can get somebody else to fix my syntax.
Probably likes to do FPGA.
Yes, I know. Yep.
And I guess Vitaly's essentially been accepted for the people.
Yes, he has.
Oh, he's going to get a PhD.
Yeah, he's going to be in a rival program though.
With Tolga.
No, well, he's going to be in 6, but Tolga's not really a rival person. He works with us well. Connor. It's just that, okay, Susan, and I'm trying to figure out who's dinging, and Josh. Why don't I just call roll since it's all kind of jumbled now? Hamad, Xingyu, and Shujian, and Yu Hao. Okay. We're recording. This is exam review day. Yeah, I've got to stop using the phrase, I'll just get a grad student to do it.
It's almost a catchphrase.
It is.
He's trying to stick.
And the next thing I know, I'm stuck doing everything, right? Okay, so project 2 was due today. That meant you had to turn in your hand-drawn timing diagram. I will stop regrades on project 1, and whenever I get to grading project 2, I will get to grading project 2. And if you want me to regrade it, just let me know if you've made some amazing progress on it. The midterm exam is Tuesday or Wednesday by appointment. I will try to work with you. I don't have any late afternoon appointments because I'm always in class in the late afternoon. And I'm pretty worn out afterwards. Pre-lecture 16 is due on Thursday. I went ahead and opened it if you want to get anxious, if you're anxious about it. We won't cover the material for pre-lecture 16 until after pseudo spring break. When pre-lecture 17 is due. We're a little bit ahead on the pre-lectures. Yeah, so Flash starts March 23rd, which puts us exactly back on schedule. What?
Maybe watching.
No, we're going to talk about semiconductor physics during pseudo spring break. Okay. Yeah, we will actually go through the calculations to figure out this is how you derive the threshold voltage of a transistor. Oh, somebody's excited. Is this recording going to be posted by this weekend? I really hope so. If I sometimes get behind, I will try to do it tomorrow or maybe even this afternoon when I'm in my meeting. I'll try to get it posted early.
So Josh just needs it right now.
Yeah, what? Okay. So, and on the exam, there's basically 5 questions. You can choose 4. I'm just going to call it open book, open notes for this semester and leave all the rest of that stuff down there. Make sure you organize your thoughts and actually do study. If you're, I've seen people do this. If you're flipping through 800 pages of notes, you're probably not going to find what you're looking for. Okay. It's always a good idea to try to get it down to a couple of sheets of notes, at least an index to all your slides and everything. You can use a calculator, but it's not going to be necessary for most of the problems. Again, there's 5 problems on the exam, and you can pick any 4 out of the 5 to be graded. On the front page, there's a little thing. There's a little table that says 1, 2, 3, 4, 5, and either circle 1 or put an X through one of them, or circle 4 of them and make one of them different somehow so I know which one not to grade. I'm not going to go through and grade the whole thing. I'll just pick a page at random if you don't X that out. It'll be whichever page I don't like grading the most. Um, this is on the front page. I've got the powers of 2.
Excellent.
I've got the permittivity of free space, and that's in farads per meter and also in farads per centimeter. And I've got, and if you need a relative permittivity, I will probably put it on there. And the capacitance, the calculation for the parallel plate capacitance is always epsilon, which is epsilon naught times the relative epsilon times the area divided by the thickness, but between the plates, distance between the plates. Okay, what are we gonna do? Okay, so we start out with a memory, and in order to avoid making a 1 terabyte long memory, we make them in squares. So it's a 2D array, and this 2D array has columns, and it has rows. And the way we address it is we give it a row address and a column address. And if both of those are true, we're going to address that single M bit. Or if it's a word or something like that, where it's 64 bits long, we'd address 64 bits with that one address. Coming into the chip, I'm going to need the addresses for the location I either want to read or write. I'm going to have the data going in or out, whether I'm reading or writing. And I've got some control signals. And a lot of these modern memory chips look a lot like microprocessors, where they have control registers, they have for different things that you have to set up beforehand. If you have something like the the Cyclone 5 board, there is a DRAM on there, and it's already pre-set up for you, so you don't have to do that. Which makes it a little bit more inconvenient because you can't go in there and change things as easily.
Unless you're Jack and you decide to make the DRAM off.
No, Jack didn't even do that. Yeah. Ian Burke actually tried to do that, go in there and mess with the control registers. And basically all we got on the board was this memory maker thing that would allow you to change certain parameters within the DRAM, like refresh, but it wouldn't let us set refresh to a really, really long time. So I hacked into the analog side of the chip and figured out how to make it by carefully messing around with the power supplies, how to make it do what I wanted it to do. And it wasn't that careful. It was kind of brute force. And then Jack just did standard memory writes. So we've got these control signals coming in. If you are the guys who write the modules to read and write from memory, they're usually starting from somebody else's work. And because it's a lot of work to do, because you got to get all the control registers right, you got to get everything set up. So they're starting from somebody else's code and they're modifying it to meet their needs. That's most of engineering right there, summarized. The row address has to go into a row decoder. And what this decoder does is it takes, if it's, let's say, 10 bits of row address, that would be 1024 different rows. It takes those 10 bits on the input and makes it into 1024 word line drivers that drive each of the individual rows. And whichever row is addressed will be the one that we turn on with word line. Same thing with the column decoder. We've got to be able to decode the column address. The column's a little bit more complicated because we both read data on the column and we write data to the column. So when we're reading data from the column, whichever bit's addressed has to be able to drive this bus and its sense amp. And before that happens, we have to pre-charge that column to VCC2. Should be familiar from your project. And when we're writing to it, we're just going to drive the column line to whatever we want it to be. This M-bit will be on, and it will add charge to that M-bit capacitor or take charge off of it as needed. That's the whole overview thingy. These are the different types of memory cells. This is SRAM. We use this for cache inside of a processor. It takes the heat of the processor just fine. It's amazingly fast, but the problem is there's 1, 2, 3, 4, 5, 6 transistors for every SRAM cell. It's basically a latch. It's also volatile. We're not going to talk about SRAM a lot in this class. It's kind of an old technology, and yeah, well, it is very useful for fast memory. If you're building your own microprocessor and you want to put a register in it for storage, immediate values, this is what we use. We just don't use a lot of it. This one right here is a DRAM cell. It's not as fast as SRAM. This is maybe like, I don't know. DRAM, you can probably get the data off of it in about 10 nanoseconds or something like that. This, you can do it in about a nanosecond. The read and write times are fairly well balanced. It's volatile, so it loses its memory. I know the answer to this. It loses its memory it's somewhere between 10 milliseconds and 2 hours after the data is turned off, after the power is turned off.
10 minutes and 2 hours?
Between 10 milliseconds to maybe like 2 hours.
Huh.
They all have their own individual unique decay rates.
Yeah.
Okay. When they refresh the cells, they're refreshing them based upon whatchamacallit. They want all the cells to maintain their memory, 99.9999%, and maybe one that they have to error correct. So it does lose its memory after a finite amount of time. This is flash, and right after the exam and after we do semiconductor physics, we'll get into flash memories, and we won't go through the whole chip design for flash. We'll talk about what this weird transistor with the double line on it means. It's basically a floating gate. The problem with this one is that the problem is it's amazingly slow. It may take microseconds to program a single cell. It may be like milliseconds, but the average rate is like in the microseconds. But it's non-volatile. It keeps its memory even if the power's off. So this is what we use for SSDs and things like that. This is like permanent storage or semi-permanent storage. Good for 10 years. EEPROM is another technology we're not going to talk about much in here. Basically, we just cut fuses to decide whether this is a high or a low. It's permanent once we do that. And this is FRAM. It is one of the emerging memories. It's kind of falling behind ReRAM and MRAM. Both have commercial applications, and we're working with those in the lab, so that will be the types of memory that I talk about next.
Very, very similar to DRAM.
I can't tell the difference between that and DRAM. They use a funny symbol for the capacitor. That's the only difference, and I don't know.
And you said so D is EEPROM, right?
No, D is EEPROM. And F is FRAM. It's ferroelectric RAM. I did find one company when I was doing some research into this a couple of summers ago. I found one company in Germany that's basically trying to sell the technology to people, but they don't have any hardware yet. So memory array size. Remember the homework problem where you had to take. This is a good review problem. The homework for your exam, the homework problem where you had to take a memory, let's say 64 meg, let's just make up a problem here. 4 banks, 512 K-bit subarrays, and we read out an 8-bit word. Word readout. So we want to draw a map of this. I'm just making this up. Okay, so 64 megabyte. The banks are the highest level of division I have on the memory. So I'm going to, and I'm just froze.
This doesn't happen a lot.
What?
This doesn't happen a lot.
Yeah, it doesn't, it happens all the time in my other classes. 64 megabits, 4 banks. I'm going to write this down. 512, and go ahead and write this down yourself because I'm just going to start babbling when I get back. No, that's okay. Subarray, and 8-bit word, because I'm just making up this problem as I go along. It's similar to a homework problem we did, and I'll be back in a momento.